Can you juggle a jam-packed schedule and still find enough rooms for every meeting? Meeting Rooms 2 is a Pattern Mastery 100 favorite and a must-know at Google, Amazon, and Meta. Over 35% of candidates get tripped up by overlapping intervals and efficient resource tracking. Master this, and you'll be set for any scheduling, heap, or interval-based interview problem. Let's break down Meeting Rooms 2 using the basic approach, so you can solve any resource allocation or interval overlap challenge step by step. You're given an array of meeting time intervals: start, end. Return the minimum number of conference rooms required for all meetings. List of intervals, unsorted, each as start, end. Integer, minimum number of meeting rooms needed. Picture running an event center. How many rooms do you need to make sure every meeting can happen without conflicts? Interviewers might ask, how do you efficiently track the maximum number of simultaneous bookings in a day? What's tricky? Intervals can overlap in complex ways. Tracking active meetings efficiently is key. Use a min heap to always know which room is free next. Sorting is crucial for an optimal solution. Sort all intervals by start time. Use a min heap to track meeting end times, smallest end time on top. For each meeting. If the current meeting starts after the earliest ending meeting, that room is freed, pop from heap. Otherwise, allocate a new room, push end time to heap. The heap size at any moment tells you how many rooms are in use. Let's clarify. Heap contains the end times of all ongoing meetings. Always pop from heap when a room frees up, i.e., when a meeting ends before the next starts. Edge cases. No meetings, 0 rooms. All meetings overlap. Need as many rooms as meetings. Sort intervals by start time. Initialize a min heap, priority queue. For each interval. If heap is not empty and interval starts greater than or equal to heap 0, earliest end, pop from heap. Push interval's end time onto the heap. After all meetings, heap size equals rooms needed. Let's try to implement it using Solution 1. Efficiency Overview. Time complexity is big O of n log n due to sorting, and space complexity is big O of n for storing the heap. Concept discussion. We are solving the meeting rooms problem using a min heap. First, we sort all meetings based on their start times. The core idea is to simulate the scheduling process. The min heap stores the end times of all meetings currently occupying rooms. Whenever a new meeting starts, we check the earliest available room, which is the minimum value in the heap. If the new meeting starts after that room is free, we can reuse it. Otherwise, we allocate a new room. The final size of the heap represents the total number of rooms required. We start by defining our function and handling the initial setup. If the intervals array is empty, we return 0. Otherwise, we sort all meetings by their start time and initialize an empty heap to track ongoing meeting end times. Next, we define a min heap push operation. When adding a new meeting's end time, we append it to the heap and then perform a bubble up operation. This ensures the smallest end time is always at the top of the heap, representing the earliest room to become free. We also define a min heap pop operation. When a room becomes free, we remove the top element, which is the earliest ending meeting. We replace the root with the last element and perform a sync down operation, maintaining the heap property. This ensures the heap always accurately reflects the ongoing meetings. Now, we iterate through all sorted meetings. For each meeting, we first check if the heap is non-empty and the earliest ending meeting ends before or at the start of the current meeting. If so, we pop from the heap, freeing that room. Regardless of whether we reuse a room or not, we push the current meeting's end time into the heap, representing the room being occupied. Finally, the size of the heap after processing all meetings gives us the maximum number of simultaneous meetings. This represents the minimum number of rooms required. And that's how this algorithm works. We first sort the meetings, then manage ongoing meetings with a min heap, reusing rooms whenever possible by comparing start times to the earliest available end time. Efficient, simple, and elegant. Let's test the function with intervals, 0, 30, 5, 10, 15, 20. Meeting 0 to 30 goes in the heap, 30. Meeting 5 to 10 overlaps push 10, 10, 30. Meeting 15 to 20 starts after 10 ends pop 10, push 20, 20, 30. Heap size is 2, so we need 2 rooms, and the program outputs exactly 2. Let's try to implement it using Solution 2. Efficiency Overview. This approach runs in big O of n log n time because of the sorting step, and it uses big O of n space to store the start and end times separately. Concept discussion. This solution uses the 2 pointers technique. The main idea is that a new room is only needed if a meeting starts before an existing room becomes free. To track this, we separate all meeting start times and end times into 2 separate arrays and sort both of them individually. We then iterate through these arrays simultaneously using 2 pointers, counting overlaps. If a meeting starts before the earliest ending meeting finishes, we increase the room count. Otherwise, we move the end pointer forward, effectively freeing up a room. First, we prepare the 2 arrays, one for all start times and one for all end times. Sorting them ensures that at any moment, the start pointer sees the next upcoming meeting, and the end pointer sees the next meeting that finishes. This is essential for accurately counting room requirements. Next, we iterate through the start times. Each time a meeting begins before the earliest ending meeting is finished, we need an additional room. If the meeting starts after or when a room becomes free, we simply move the end pointer forward, reusing that room. After going through all the meetings, the final room count reflects the minimum number of rooms needed, and that's how this algorithm works. It separates start and end times, sorts them, and uses 2 pointers to efficiently count overlapping meetings, giving us the minimum rooms required. Efficient, simple, and elegant. Let's check how our solution figures out the minimum number of meeting rooms using this test case. The input is 7, 10, 2, 4. Each pair shows when a meeting starts and ends. We sort the start times 2, 7, and the end times 2, 4, 10. The first meeting, 2 to 4, uses 1 room. The next meeting starts at 7, which is after 4 ends, so we reuse the same room. Total rooms needed is 1, and the program outputs exactly 1. Breakdown recap. We're given an array of meeting intervals, each with a start and end time, and we need to return the minimum number of rooms required so that all meetings can happen without conflict. In short, it's all about finding the maximum number of meetings that overlap at any point in time. Assess recap. The challenge is tracking overlapping intervals efficiently. Instead of checking every pair, we sort the meetings by start time and use a min heap to keep track of ongoing meetings by their end times. The heap helps us know which room will be free next. If a new meeting starts after the earliest one ends, we pop it off the heap, that room is now available. Otherwise, we push the new meeting's end time, meaning we need another room. The heap's maximum size during the process tells us how many rooms are needed. Structure recap. We start by sorting all intervals by start time. Then, we initialize a min heap to store end times. For each meeting, if the heap isn't empty and the current meeting starts after or exactly when the earliest one ends, we free that room by popping the heap. Then, we always push the current meeting's end time. Once all meetings are processed, the heap size equals the number of rooms required. Implement recap. We implemented this using Python's heap key module. It ran efficiently, with a time complexity of O(n) log n, from sorting and heap operations, and passed all tests smoothly. Check recap. We verified the logic using multiple test cases. For example, 0, 30, 5, 10, 15, 20 needed 2 rooms, while 7, 10, 2, 4 only needed 1. Even edge cases like no meetings or fully overlapping schedules produce the correct results. Closing insight. The key takeaway? When dealing with overlapping intervals, sorting plus a min heap is a powerful combination. It's not just about detecting overlaps, it's about managing them efficiently, one meeting at a time.